Good afternoon, Kohli. Wait, good afternoon, sir.
Altaf, how are you?
Good. Danny.
Hi Abbas, how are you?
Hi, Dr. Jangi. I'm fine. Thank you.
Welcome,
How are you?
Bas.
Yeah, I'm good. Hi Altaf.
Yeah, I said,
I think there's a problem with your sound system again. Uh,
Yeah, welcome, Abbas.
Hi, thank you.
So today's
Nice to
session
meet
will be run, by both of us. So Abbas is doing a PhD with me. So he is now in his second year, and he is working mainly on power system planning with hydrogen and some operation as well.
We'll start in 5-10 minutes.
Yeah, definitely. So, but we'll be waiting another 5 minutes.
Okay, no problem.
We can
Okay, then. So Abbas, can you please share your screen?
Yes. Yes.
Hi everyone, good afternoon. As I mentioned yesterday that today we'll be talking on green hydrogen. So initially, Abbas, he will talk about some background, potential hydrogen technology, and also like the power system planning. Mainly the expansion planning with hydrogen, and then myself. After that, I'll be talking about hydrogen from different countries' perspective, and also I will show you a small feasibility study that we have done at Sydney for having a possible hydrogen hub. So as mentioned previously, if you have got any question or comment, feel free to interrupt us at any time. And Abbas,
Yes.
like every 10-15 minutes, you just pause and ask them whether they have got any question or comments.
Okay. Sure.
Okay, then when you are ready, you can start.
Can you see my screen?
Yes, I can see your skin, and also Altab, I think you can see the skin as well, right?
yes. Screen is visible and he's audible also.
Thank you.
Hello, everyone. Welcome to my presentation. As you can see, the projects that I have done under the supervision of Dr. Jahangir is entitled as Integrated Distribution Network and Renewable Hydrogen Refueling Station Expansion Planning. And in this problem, we will focus on the expansion planning of uh, distribution electricity systems, as well as renewable energy sources, specifically wind farms and solar farms. And also, we will try to develop hydrogen refueling stations for fuel cell electric vehicles. Today, first of all, we will take a look at the introduction of this research work, and then we go for the background, and then we investigate different types of hydrogen technologies which are related to the hydrogen production and hydrogen storage units. And then we will go for challenges, and after defining our research problem, I will show you the simulation results, and I will show you 2 case studies. And then finally, I will come up with the conclusion part. If I wanna briefly talk about this project, it is worth mentioning that in this project we have presented an integrated multi-stage and multi-zone distribution network expansion planning, and in this problem we will consider the development of renewable energy sources, including wind farms and solar PV panels, as well as the green hydrogen refueling stations, which are which can be in the network. And in fact, we have an electricity network which is intertwined with the transport sector. The benefits of this project can be described in different ways. First of all, it can be helpful to distribution system operators because they can develop power distribution networks to address the growing demand of electricity loads economically, reliably, and also in a safe manner. Moreover, it can be beneficial to integrate renewable energy sources in an optimal manner. Moreover, it can provide a great opportunity to develop green hydrogen refueling station networks to deal with the growing fueling demands of fuel cell electric vehicles in the network. In addition, this project can be helpful for the government because it can facilitate the fulfillment of Australia's zero emission targets. Because Australia is trying to go to the zero emission networks by 2050, and it tries to fulfill their targets. This project, there are different entities that can benefit from this project, and they are the governments as well as industries, and also different types of communities, such as research communities, and also people in the society who who are the owners of fuel cell electric vehicles can easily use hydrogen refueling stations, which are work which are working with renewable energy sources for producing hydrogen. As you can see in the left figure, according to the Australia's emissions projection in 2080, Australia aims to reduce its carbon dioxide emission by 26% from 2005 to 2030. And Australia tries to reduce its carbon dioxide emissions in 2030 to reach the 563 megatons of carbon dioxide emissions. On the other hand, in the right hand of this screen, we can see another figure, and as you can see that electricity and heat, as well as the transport sectors, are playing a significant role in producing carbon dioxide emissions worldwide. Therefore, on the other hand, we can consider them as great opportunities for decarbonization. For example, in Australia, after coal, the largest share of electricity comes from renewables. And among different types of the renewables, we can see that wind and solar energy are mostly used in Australia for producing electricity. Therefore, it can be said that Australia is well placed to incorporate renewable energy sources like wind turbines and solar PV systems. On the other hand, we talked about the transport sector, and in the transport sector, in order to decarbonize this network, the transport network, recently many researchers have done many works. They have come up with battery electric vehicles, and recently they are going towards fuel cell electric vehicles. And there are some benefits that fuel cell electric vehicles can have over battery electric vehicles. First of all, is that fuel cell electric vehicles have a short refueling time. For example, it takes from 4 to 5 minutes to fill a hydrogen tank. On the other hand, battery electric vehicles, when they are in the fast charging mode, it takes about 20 to 30 minutes to charge the batteries. Moreover, fuel cell electric vehicles have the larger driving range, and they can their filled hydrogen tank uh, can be used for approximately around 500 to 550 kilometers. Another important factor is that they have higher resistance to depletion, and the main reason is that regarding battery electric vehicles, the lithium batteries are required to be exchanged several times, and it can lead to degradation. Therefore, in this research project, we will focus on two different sectors, electric distribution sector and network, as well as the transport sector. When If we want to go toward the progress and development of electric distribution networks, we can say that previously and traditionally, energy systems from power generation to load demands were one directional, and they call them conventional distribution network. However, uh, during the time, with the pass of the time, the conventional distribution networks are replaced by active distribution networks, and nowadays we can have active distribution network can be reconfigured. It means that a lot of switches can be installed, uh, and feeder sections can be disconnected, and the flow of electricity can change over the feeder sections. However, regarding the transportation network, there are some factors that are important for us. First of all, is that we need to develop hydrogen refueling stations in order to support fuel cell electric vehicles for their owners. In addition, we need to produce hydrogen, specifically green hydrogen. And then also we can use hydrogen storage units in order to increase the flexibility of our networks. As I mentioned, in the first figure, you can see the conventional distribution network, which is a one-directional system, which can be from power generation to the load demands. However, with the introduction of smart grids, active distribution networks are replaced this conventional system, and these conventional systems are called passive systems. However, the active distributions systems can provide a great opportunity for distributed energy resources such as distribution generations, like wind farms or solar farms or other conventional DGs, as well as energy storage systems or demand response programs uh, to inject electricity to the network. And therefore, the consumers are considered active um, active demands, which can distributedly produce electricity for their needs. And the third figure also shows the reconfigurable active distribution networks, and these switches can be disconnected and the flow of electricity can be changed. When it comes to the hydrogen technologies, first of all, hydrogen production is very important for us. There are different types of hydrogen which can be produced, and depending on what technology is used for them, they are called different names. And we have gray hydrogen, blue hydrogen, and green hydrogen. Gray hydrogen as you can see, they are produced by fossil fuels. And two common methods for producing gray hydrogen is steam methane reforming and coal gasification. Unfortunately, these approaches, although they are well established and mature, however, they produce lots of carbon dioxide emissions. Blue hydrogen also is produced by fossil fuels. However, an extra approach called carbon capture and storage technique is utilized to capture the produced carbon dioxide emissions. However, inherently, also they are not uh, free of carbon dioxide emissions. Recently, green hydrogen have gained very uh, much attention these days, and one of the most popular approaches of producing green hydrogen is utilization of water electrolyzers. And in this process, which is called water electrolysis, the electricity can be used to break the water into hydrogen and into oxygen, and then the produced hydrogen can be used for a wide range of applications. Here you can see the water electrolyzers, and as you can see, the electricity which is coming from renewable energy sources can split the water into oxygen and hydrogen. And because this hydrogen is produced using renewable energy sources, uh, such as wind farms or solar PV panels, we are calling them green hydrogen. Water electrolysis process have several benefits. First of all, it can provide a great opportunity to bring a scalable, flexible, and distributed option for hydrogen production. It means that hydrogen can distributedly produce in different areas, and we don't need to have a centralized unit for producing hydrogen. In addition, it can enable high implementation of renewable energy sources. For example, during um, the day when the solar, for example, in Australia, the solar power is much more than the electricity demand of the network. Uh, we need to curtail this excess solar power, and it cannot be beneficial, and it can also endanger the investment in installation of renewable energy sources. Water electrolyzers can enable leveraging the excess solar power for producing hydrogen, and we don't need to curtail the excess solar power. In addition, in other words, we can increase our electricity demand by producing hydrogen. Moreover, it can also, as you can see, because it is called a green hydrogen, as it is produced by renewable energy sources. It can provide considered as a green energy carrier and clean. There are different types of technologies for water electrolyzers. However, the three main types of electrolyzers are proton exchange membrane, uh, alkaline, and solid oxide. And according to the electrolyte material which is used in them, uh, they are called different names, and they have different technologies. In this figure here, you can see the technology readiness levels of different types of water electrolyzer technologies. And as you can see, the alkaline electrolyzers as well as PEM electrolyzers are the most matured technologies among different types of water electrolyzer technologies. And nowadays, these two technologies are used mostly. If we want to compare these water electrolyzer technologies, alkaline electrolyzers and PM electrolyzers, we can see here that when it comes to the advantage of alkaline electrolyzers, we can see that they have lower capital costs. In fact, they are more mature than PM electrolyzers. Um, in addition, also they are well established, and when it comes to their disadvantages, they can produce larger footprint. Moreover, they have also low pressure hydrogen product. They are considered low pressure hydrogen product. However, PEM, which have gained much more attention these days in comparison with alkaline electrolyzers, have more advantages because they are very smaller, flexible, and modular. Moreover, they faster dynamic response can enable them to easily be connected to the renewable energy sources. Moreover, they have higher current density as well as higher purity hydrogen. The only problem is related to their higher capital costs. However, I think with the pass of time, they can be mature and their capital costs can decrease. In this table, you can see the price of the levelized cost of hydrogen, which is produced by these two technologies. You can see that the levelized cost of hydrogen is between 4.78 to 5.84 per kilograms of hydrogen. However, regarding the PM, its levelized cost is between 6 to 7.50 per kilograms of hydrogen. After considering the hydrogen production technologies, specifically the water electrolyzer technologies, we need to consider hydrogen storage technologies because they are required to be installed in the system in order to store the produced hydrogen, and then they can be used later during the day. For example, we can say that we can produce hydrogen during midnight when the electricity price is very low, and then we can store them in the hydrogen storage systems. And then during the day, when the request for and the demands for hydrogen energy are very high, we can use them. However, they are different types of mature technologies related to the hydrogen storage. The first one, they are pressurized hydrogen storages, and they are considered as mostly common hydrogen storage, and they are used mostly in the network. However, unfortunately, they have lower density, and they need to be liquefied, or they need to be pressurized more and more, and it can lead to some extra cost. Regarding the liquefaction, it means that we provide a liquefied hydrogen, and another one is related to the material carriers. Material carriers, it means that we can produce hydrogen and we can convert them into another chemical material, specifically ammonia, NH3, and we can uh, it can provide an advantage related, because it can have a higher hydrogen density. Moreover, it can be transported very easily and mostly in Australia it will be used for export to other countries, especially neighboring countries such as Japan, China, and something like this. The drawbacks of ammonia, for example, can be that they may retain additional energy penalty and cost associated with the recovery of hydrogen from the carrier molecule. It means that when we, for example, transport ammonia from Australia to Japan, or to other places in Australia for different applications, we need pure hydrogen, and we need to perform some chemical process in order to separate the pure hydrogen from the ammonia, and it can be costly, and also it may lead to also some it can produce some emissions.
Abbas, I mean, just like
Yes,
asking the attendees whether
sure.
they have got any question or comments so far what Abbas has presented. Any question or comments from anyone?
Sir,
Yes.
sir, can we use this hydrogen technology as one P2X technology?
Definitely you can. That's a
Yes.
power 2x. That's completely possible, and that's the way. I mean, different country, including Australia, was also heading.
Okay.
Because it could be, almost utilize almost all sector.
Yeah.
That's why, power 2x. Yes. Any other question or comments?
Compare battery storage systems and fuel cell.
Yeah.
Sir, which is more advantageous? Because most of the work we are doing for EV applications, PV with battery or grid with battery. And so nowadays we are seeing literature with the fuel cell.
Yeah.
So which is more advantageous, sir? And
Well, I mean, in terms of advantages, like fuel cell has got the highest energy density. So even it's higher than battery. And also if you think about EV, application, then for light vehicles or buses with short distance travel, battery based vehicle, might be okay. But when you have got heavy vehicles that also have in a long distance travel, for example, if you think about the truck, which is transporting food or other materials from one state to another state, in those cases fuel cell based vehicle would have better advantages than battery based vehicle, because you don't have to recharge the battery. And as you know that, if you don't have, fast charging option, you need a quite bit of time to charge the battery. But for like fuel cell based vehicle, it's just like the normal vehicle. When you take the petrol, it will take like the same system, like just to have the hydrogen, and then you can travel like higher distances. And also like
Yes, sir.
even other advantages as well, like the country like in Australia. So as I mentioned that we have got additional renewables during the peak hour. So if we don't utilize that one, and that is already happening in Australia, there are like some like mandatory power curtailment from the renewables during the off-peak time. So why not, use that off-peak, energy and just to produce, hydrogen, and then, it can be exported to other countries. So this is like, some of the advantages, but there are, other advantages. And having said that, there are many challenges as well.
Sir, when we use fuel cell, like as you said, like how we fill the petrol, we can fill the hydrogen, you said. I agree, sir. But like what are the any precautionary measures we have to take as a common man, sir? Because
Well, as I said, like, there are many challenges, as I said, like, and safety, that's a definitely a issue for, hydrogen, because, the hydrogen is a flammable gas.
yeah, that's it.
So if you're driving a car and if there's an accident and, your tank is having fire, then, it is dangerous for like, all the passengers who are in the car. And also in terms of the pricing, still, hydrogen price is higher than other source of energy. And the technology readiness, technology maturity, and also like still, there should be further research and improvement in the technology side.
Okay.
Um, so in most of the cases, we expect that by after like 2030 or 2040, hydrogen will get uh, the market, because by that time, that price will be comparable to other technology. And also the technology readiness for um, you know hydrogen technology, will be measured and comparable to other technology. But
Thank you, sir.
currently, still there are many challenges.
Thank you, sir.
Thank you.
Sir,
Yes.
sir, since hydrogen is actually combustible, uh, why don't we just use something kind of an IC engine that is powered by hydrogen, but instead, why would we like to convert it, uh, power a fuel cell and then use to drive the vehicle, sir?
Well, as I mentioned, when I was talking with electric vehicle, that the problem with IC engine, because its efficiency is very low. Um, so that's why, we don't prefer that vehicle, because it has got very high losses. So while we have got hydrogen, there is no point going to, like, drive that IC engine, because it's still, you're using, hydrogen as a fuel cell. So still it will have that safety issue. But having said that, that it is a safety issue, but the way that technology is progressing, I mean, I believe that in the next 5 years, as I said, the technology will be much more matured, and that, safety part, that would be also like, in the very high level. And as Abbas mentioned that, uh, I mean, hydrogen is not only that, I mean, only we can store as a, I mean, gaseous form. We can store in other form as well.
Yeah, of
And
course.
then we can transport and, use like, for many other application in different countries. So this is not only gas, but it could be, in other form as well.
Okay. Yes, sir. Got it.
So like liquid, I mean, it could be stored like a liquid and other form. So and the material carriers that Abbas already mentioned, like ammonia, that is like one of them.
Yes, sir. Got it, sir.
Thank you.
Hello, Professor Jahangir. So, but the cathode material or anode, which is made from platinum, this is also very costly. Means it is increasing the cost. Do we have any progress? Other material are coming.
Well, I think you're right that, I mean, anode and cathode are costly, but even like the catalyst that use, for the fuel cell, even that is even like, much higher costlier than the technology that we use, I mean, material that we use for anode and cathode. So that is, I mean, one of the reason that the price is high. That's why this is not, I mean, that much popular. But as I say, like, when we have got like huge amount of, I mean, hydrogen energy is being used, that time actually the price will go down significantly. Like that's already some cases and some study have been done, like for example, Europe, and they have shown that like if they have got like 40 gigawatt, even the price would be like hydrogen price per kilogram would be like close to a $1. So, I mean, you're right that we need further research to find probably, other materials. Um, I mean, to reduce the cost, not only the materials, but also like the methodology that we use to improve the overall, like the energy efficiency. And also like we need like the market, I mean, as well. I mean, for like massive application that will drive the price down. And as I say, like there have been many studies have been done in Europe, China, USA, and even Australia, and they have, I mean, concluded that by 2040, and even like in India also, I mean, I saw that there have been one study have been done, and they have also found that even in India, by 2040, the price will be comparable.
Yeah, I think we believe that computational power increase, and then this research will search new material or this
Yeah,
electrolyte.
definitely. Because now, it's still like this is 22. So I mean, still we have got more than a decades. I
Yes.
mean, improve the technology. But there, I mean, in Australia, I know that there are so many projects going on, but not only Australia, as I say, like in other countries, even in India, also there are some projects going on. That's a good discussion. Thank you. Any other question or comments? If not, Abbas, let's continue.
Okay. Here we talk about different methods of hydrogen storage, which were compression, liquefaction, and material carriers. Regarding the compressors, there are different technologies which can be used. As you can see, low pressure tanks or pressurized tanks, underground storage, or line packing are different types of technology that can be used, and each of them has their own pros and cons. As you can see, for example, low pressure tanks have they are more mature than other one. However, the only drawbacks of them could be that they have poor energy density. Regarding the pressurized tanks, if we try to if we want to compress the low pressure hydrogen, we need to use, for example, some cascade compressors and in different stage in order to reach our intentional pressure. However, again, their energy density are also low, and although they are established technologies. However, underground storage, they they can be produced at a high volume of hydrogen and at lower pressure and cost. However, the only problem is that we need a specific uh, geographical environment and a space for them, and it cannot be applicable in every places.
Yeah, and for electric vehicle application, probably, the most desirable option would be the pressurized tank, because that will have higher energy density, and that will need like a lower tank size. Thanks, Abbas. Please
Yeah,
continue.
thank you. And also another option can be line packing, and this means that hydrogen can be blended into the natural gas in the existing natural gas pipelines, and also they can be stored there, and then uh, they can use later during the day. However, it is important to mention that currently researchers and workers are trying to blend hydrogen into natural gas pipelines. And also they are trying to come up with new pipelines so that they can be able to carry pure hydrogen. However, certainly it needs new infrastructure and installation and investment in installation of new pipelines and infrastructures, and it can be really costly at this stage. However, in the future, uh, they may become more mature. Regarding the liquid hydrogen that can be stored, we have different technologies, cryogenic tanks as well as cryocompressed tanks. And you can see here their advantages and disadvantages. Both of them, when it comes to the disadvantages, they need advanced and more expensive storage material. Uh, and regarding the liquid, when liquid hydrogen is stored in these types of tanks, uh, in fact, the main problem is that they can experience loss of energy, and some liquid hydrogen may be evaporated, specifically during the transportation and something like this. And the material based one, as I said, it is ammonia, and you know, hydrogen first is converted to ammonia through the Haber-Bosch process, and then it can be easily transported to other places. Especially, they are more convenient for exporting to other countries because they can be transported at room temperature and pressure. However, the only problem and disadvantage could be that at the point of use, we need to again convert it back the ammonia to the pure hydrogen, and it can lead to extra costs. Today's the technology are going toward emerging hydrogen storage systems, and one of the new and also emerging hydrogen storage technologies is metal hydrides. And in fact, in metal hydrides, hydrogen is bonded to the metal alloy, and it can be stored in this metal hydride systems. And one of the first products which have used the metal hydrides for hydrogen storage is the Lavo company, and the Lavo product, and in fact the Lavo product is suitable for small case applications, specifically for residential houses as well as other commercial or business users. You can see here that they can be easily installed in houses or businesses, and they can be connected to the renewable energy sources, specifically solar PV panels. And then, as you can see, this electricity which is coming from solar PV panels is able to split the water into hydrogen and oxygen, and they produce pure hydrogen, then can be stored in these storage systems, and they are hydride storage vessels, and they can be stored here, and then they can be used again for different applications, or also they can be converted again to the electricity using fuel cell, and they can send the electricity to the networks. This system also have high storage capacity, and their storage capacity is equal to 40 kilowatt hour. Also, this company recently are working to present a new product which is suitable for large scale hydrogen storage applications. And in fact, and this product is called HEOS, and it is hydrogen energy operating system. And this system includes a green hydrogen generator. It means it consists of electrolyzer, storage, and fuel cells. And they are really beneficial for large scale applications, and specifically they can be used at utility and community scales, because they are able to store much more energy, which is equivalent to 13 megawatt hour. And also they can be easily connected to the uh, uh, on-site wind farms or solar farms. Again, in this product, the technology of metal hydride is used. When it comes to the challenges and gaps of this research work, first of all, we have the distribution electricity network, and on the other hand, we have the transport sector, which contains fuel cell electric vehicles. Therefore, during the time fuel cell electric vehicle market will develop in the transportation system, and with the increasing fuel demands for fuel cell electric vehicles, we may have some new challenges to produce hydrogen and supply the fuel cell electric vehicles. Also, on the other hand, in the electricity network, especially in Australia, during the day, we have additional renewable power generation, and it can be challenging. However, the solution is that we can use these extra renewable power generation for producing hydrogen using electricity. And one of application of this hydrogen can be mobility, or in other words, fuel cell electric vehicles. In order to support fuel cell electric vehicles for the owners, we need to develop green hydrogen refueling stations uh, in different places of the transport sector. The other challenges are relating to the electricity network. When we want to produce the green hydrogen, we need to implement renewable energy sources which are located in the electricity network. And also, on the other hand, with the pass of over the time, we will experience growing power demand as a result of an increasing population or other reasons. Also, we may experience the growing hydrogen fueling demand uh, with the when they are more established. And also, in order to deal with these challenges, we need to appropriately try to find the optimal site and size, and also the time during the decades for the installation of hydrogen refueling station or new renewable energy sources in the system. In fact, we need to coordinate the operation and installation of these technologies together. Therefore, in this research work, we try to present a new multi-stage and multi-zone expansion planning model for distribution systems. And in distribution systems, we try to find the optimal size and optimal location for renewable energy sources, which are used to supply electricity demands, and other groups which are used to supply uh, hydrogen refueling stations for producing hydrogen. Moreover, in this problem, we have supposed that hydrogen refueling stations are able to produce and supply their needed hydrogen. And in other words, hydrogen can be produced distributedly. In this problem, we have three separate main aims. One aim is related to the distribution network asset. Another aim is related to the green hydrogen refueling station, and another one is related to the renewable energy sources, including wind farms and solar farms. When it comes to the distribution network assets, we try to find the optimal location and size and timing for the construction, replacement, or reinforcement of distribution network assets. Assets in the distribution network include feeder sections or substations. And feeder sections in the distribution network can be categorized into three different categories. Some of feeder sections existed previously, and also they are irreplaceable. On the other hand, the other group which exists in the network can be replaced by uh, new feeder sections with higher capacity, for example. And also there are other groups of feeder sections which are candidate for construction, and they are ready to be installed in the network. It is similar for substations, and we have existing substations and also substations which can be reinforced to increase their capacity. as well as there are other substations which are candidate for construction in the electricity network. Also, regarding the green hydrogen refueling station, we need to try to find the optimal location. The location, it means that we find the optimal, we find the best electricity nodes for installing the hydrogen refueling station. And also we will try to find the optimal size and also the timing for construction of refueling stations. Moreover, in order to deal with and address the fuel cell electric vehicles fueling needs, we need to divide the network. The network means the electricity network, which is intertwined with the transport network, can be divided into multiple zones. And then regarding the fueling requirement of each zone, we will want to find the optimal number of hydrogen refueling stations, their size and location, which can be useful to address the fueling demands of fuel cell electric vehicles. In addition, we need to coordinate finding the optimal location and sizing and timing for construction of renewable energy sources, including wind turbines and wind farms. We have two groups of renewable energy sources. The first group are renewable energy sources which are distributed throughout the distribution network, and another one are those which are designed to locally supply the electricity demand of uh, hydrogen refueling stations production unit. And the production unit means that they can use water electrolyzers for producing their hydrogen locally. This can be a good example, and as you can see here, we can have the electricity network which is intertwined with the transport sector, and we can see that this system is divided to the two zones, zone 1 and zone 2, and we can see that depending on the hydrogen fueling demands of fuel cell electric vehicles. For example, in this zone, only two hydrogen refueling stations were required to be installed. On the other hand, in zone 2, depending on the population and as a result, their fueling demands of fuel cell electric vehicles, only one green hydrogen fueling station was required to be installed. And as you can see here, we have water electrolyzers, uh, tank storage, which are used in the hydrogen refueling stations, so that in order to increase their flexibility. If we want to define the problem, this problem includes one the objective function, and in this objective function, the distribution system operator try to minimize the total cost of investment, energy production, the maintenance costs, as well as emissions costs, which are incurred over a planning period. Uh, for example, a planning period, maybe we want to plan for next 20 years, for example, or for next 4 years. It can be short time or long time or mid time. However, this objective function is subject to different types of constraints, and they can be categorized into three different groups: investment and utilization constraints, which can include the constraints related to the feeder sections, substations, wind farms, PV systems, and green hydrogen refueling stations. And the operational concerns are related to the electricity network, wind farms, PV systems, and again hydrogen refueling stations. And again, in this system, we need to meet the radiality constraint in order to prevent the loops in the distribution network. Here we have analyzed two different case studies. The first case study is a small electricity network. It includes 6 nodes, and in fact it is a 22 kV network, and this electricity network is divided into 2 zones. Zone 1, which consists of these nodes, and zone 2, which consists of node 1, 3, and 4. And here we have 2 substations, as you can see. These are substations, and which we have one existing substations, and this substation is irreplaceable, and we cannot replace it with other substations. However, this dotted substation is related to the candidate one for construction, and the dotted lines are related to the candidate feeder section, which are used for construction. And we have considered 3 planning stages. For example, we want to plan for the next 3 years. And here is, you can see the data related to the conductor types of feeder sections. And as you can see, we have 3 conductor types which can be used in the network, and you can see the characteristics of these feeder sections and the capacity, and this shows the investment cost for replacement of these conductor types, and these values are related to the investment cost for construction of new conductor types for the feeder sections. On the other hand, we have 2 types of alternatives for substations, and they can be used for reinforcement or construction of new substations. And these parameters also show the maintenance costs for the substations. The data related to the hydrogen refueling stations, we can see here that we have considered 2 alternatives for hydrogen refueling station construction, and each hydrogen refueling station type can, as you can see, has different characteristics. For example, they have the capacity of producing hydrogen during the day. It means their daily hydrogen production capacity. Moreover, it is related to the investment cost, and also in the first hydrogen refueling station type, we only consider 1 storage tanks with the minimum and maximum storage, hydrogen storage in per kilograms, as you can see. Moreover, here we can see the number of hydrogen refueling stations that are candidate for construction. We have we want to construct only 1 hydrogen refueling station in zone 1 and 1 hydrogen refueling station in zone 2, and we want to find the optimal location for each of them, and also the optimal time and size for them. The candidate place for construction of hydrogen refueling stations in zone 1, as you can see, it is nodes 2 and 5. For example, it can be constructed at one of these nodes, and we need to find the optimal location for them. However, regarding the next zone, zone 2, nodes 3 and 4 are candidate. However, when our network our network size increases, we can have more optional places for installation of hydrogen refueling stations. Moreover, here we have two alternatives for wind farms as well as solar PV panels, and each of them have the capacity of 1 megawatt or 2 megawatt, and the set of candidate nodes for installation of wind farms are node 2 and node 5. They are candidate nodes for installation of wind farms, and the candidate nodes for installation of solar PV systems are nodes 3, 4, and 5. So here I intentionally use node 5 for as a candidate nodes for installation of both wind farm and solar farm. However, we need to see which of them are required to be installed, for example, in node 5. Here show the results for different stages. This is related to the next year, the second year, and the third year. And as you can see, here we need to install new wind farm with the capacity of 2 megawatt at node 2, and also we were required to install a hydrogen refueling station, and these hydrogen refueling stations of type 2, which here show type 2 has the daily capacity of hydrogen production of 510 kilogram, was required to be installed. And in the vicinity of this hydrogen refueling station, we were required to install the solar farm with the capacity of 2 megawatt to power the water electrolyzers of hydrogen refueling stations for producing hydrogen. Moreover, two feeder sub-extensions were required to be constructed. As you can see, the type 1 with the lowest capacity were required, and its capacity was 3.4 MVA. However, regarding stage 2, we can see that another hydrogen refueling station was required to be installed at node 5, and also you can see here that a wind farm with the capacity of 2 megawatt was required to power this hydrogen refueling station. And the red one, as you can see, this actually the feeder section between node 1 and 4, which were used, the type 1, we can see here that this line was reinforced and replaced by the conductor type number 3, which has a higher capacity. You can see its capacity is 8.5 MVA. And also we can see here that the first substations are reinforced and actually its capacity was increased. And you can see here stage 3 have a different topology compared with stage 1 and 2. And here, as I said previously, we can see the reconfiguration of the distribution network system. We can see here that as you can see, the line between 5 and 2, which was at stage 2, was disconnected, and a new line was constructed between node 6 and 2, and a new substation was required to be constructed to support the electricity. Here also shows the results related to the hydrogen production for each hydrogen refueling stations. We had 2 hydrogen refueling stations, as you can see, at node 5 and node 4. This result is related to the node 4, and we can see that the pattern of hydrogen production, and they have shown the erratic pattern. The main reason is that we can see here that the hydrogen is produced, and again it's not produced for a while of time, and the main reason is the utilization of hydrogen storage tanks. And if you can see here, we can see that the hydrogen storage is replenished and then again become empty. The main reason is that the capacity of hydrogen storage tanks in this problem was chosen very small. And however, if we choose a larger capacity for them, we didn't show this erratic pattern. And here in the table, we can see our objective functions, which includes different parts, and here it includes investment costs, energy production costs, maintenance costs, and emission costs. And here you can see the total cost in each stage. And at each stage we need to invest different money, as you can see, to fulfill our hydrogen demand and as well as electricity demands. This one also is a second case study, which
Boss,
as yes,
sorry for the interruption. So you already have shown some result. This
yes,
is just like another case study. So plus before that, probably I'm not sure all the attendees have like understand what Abbas is trying to convey. So the things that Abbas has done here. So for example, let's say, I mean, if you would like to have a hydrogen refueling station, or some load that you would like to supply through hydrogen, then you need to actually have further infrastructure for your electricity network, because you will be producing green hydrogen from mainly solar and wind energy, but sometimes you can also buy energy from the power grid as well. So if you would like to do that, that would be like the additional demand coming to your power network. So that's why you need additional infrastructure to do that. And here what Abbas has done, so he has first approximated or quantified that would be the demand for that particular application, and based on that he has developed some optimization algorithm just to find out what would be the optimal sizes as well as operation of all the devices which are connected to that particular system. So having said that, I'll just open the floor whether you have got any question or comments regarding that, particular planning and operation studies. So is there any question or comments?
Do you use graph theory, or which method did you use here to solve this optimization problem?
So can you please repeat? I haven't got the question correctly.
Professor Jangir, which method do you use, graph theory, to solve this problem, or how you optimize this? In
So
the
Abbas,
previous
can
slide,
you,
there is a
Abbas, what method you have used for your optimization?
I have modeled my problem in the GAMS, and I formulated it in the GAMS, and also I used the mixed integer linear programming, yes, MILP, for solving this problem. Because we have binary variables as well as other continuous variables, and also I linearized my problem.
Okay, so from non-linear to linearize your problem. Okay,
That's right.
can we use graph theory also for this type of problem?
Excuse me, what?
Can we use graph theory from computer science?
Graph theory graph theory, no, because it is a optimization problem, and
Okay.
you need to consider a wide range of parameters and let the solvers to solve the problem for you according to the comparing the investment cost, replacement cost, and you need to consider a lot of parameters, input parameters.
Yeah, you can actually use also graph theory. I mean, if you would like to implement some, control using, some sort of communication in the system. So in that case, I mean, sometimes you have got like, leader, follower, those sort of cases. I mean, if you would like to implement the control, I think you can utilize graph theory.
No, yes, okay. Thank you. I got the point.
Yeah. Anyway, I mean, Abbas, I mean, your second application is just like the same result, just using the Australian
Yes.
real network. So I don't think, I mean, we need to, repeat again. So I have already sent the slide. I mean, if someone is interested, I mean, they can have a look. But the next one is more like using a real network in Australia. And the first one is just like, it's like an open source system, which is, used in the literature. So just for the validation purpose, I mean, we have also implemented using, network which represent, some real system, I mean, in New South Wales. So anyway, if there is no question, Abbas, thank you. I mean, you can stop sharing, and also you can, leave the meeting. Thank you. Thanks for your
Okay.
time.
Thank you everyone for inviting me. Thank you. Bye.
So I'll just give you 5 minutes break, and then I'll have like, another 30 minutes. So I'll just go through some information, as I mentioned, like considering different perspective, some of the application, although I mean, Abbas did mention some application, but I'll go through some other application. And as I said, like, we have done one, I mean, simple feasibility study just to have a hydrogen hub at New South Wales with few industry.
For all the
Anyone from
participants,
here, I mean, is planning, I mean, to work relevant to, hydrogen technology or its application, or even like doing feasibility study?
I have got inside.
Take a minute.
Yeah, Altaf, you would like to say something?
Yeah. Actually, I for all the participants, I have shared the recordings till now with you all. Also, the PPTs as they come, I am sharing it with you all. I had also shared one form which around 5 people have not submitted. So please do the needful. I'll be sharing one more form for the name and institution that you would be requiring on your certificate. So please fill that also as early as possible. And lastly, 2 or 3 people have got other than Gmail IDs. So recordings cannot be shared with them on that ID, right? So please give me the Gmail ID if possible so that I can share it with you as well. Lastly, we would be having one more lecture after 3 o'clock tomorrow on WIN connection. That will be taken by Professor Farhad Ilahi from NIT Srinagar, right? So thank you. Thank you, Jahangir sir.
You're most welcome.
I heard the news, Jahangir sir, that Saudi Arabia is going to invest a lot of hydrogen in the future.
I mean, you're right. I also saw that news, and I also saw that there are already some project is going on in Saudi Arabia as well.
They have
But although they are,
something rocks or
yeah,
something where hydrogen is there, or what? Or they are going to plant hydrogen.
can you please repeat the last part?
Is there something material so which is too much available in Saudi Arabia? Is that, or they are going to study, or they are going to put like a
I think,
plants for hydrogen?
I mean, if you think about the technology, I think they will be probably importing or buying technology from other country, and then probably they will install there. But I think just for probably that going back to net zero and the environmental reason, probably they are going to adopt this clean energy path, because they also realize that the way that other countries heading, probably it's a good time to invest in this sector. So I don't think they have got I mean materials or their local technology, but just for achieving net zero and environmental reason, I think probably they are gonna be interested for this technology. But definitely, I mean, they have got, I mean,
They
like,
put priority. Means they have big initiative they are going to take on this.
that's right. So I have got another half an hour, so I'll just quickly share, few other things on top of, I mean, Abbas has already shared. So, I mean, although, I mean, green hydrogen is new, but hydrogen is not new. I mean, as you know, that's, I mean, if you think about the current market, like 50 million tons of hydrogen that's actually produced each year. But I mean, most of them, I mean, are produced from natural gas, which, I mean, Abbas mentioned that it could be either blue or gray hydrogen. If we, I mean, either capture, stored and use, carbon, the other one, we don't capture, carbon and store it. So, I mean, there are a number of reasons. I mean, that's, green hydrogen might be popular in coming years, and one of them, as I mentioned, like that, most of the country, including Australia as well as India, they have promised that they will be going carbon neutral I mean, for Australia, I think by 2050. And if I remember currently, India have promised by 2060. Is that right? Or
Yeah, I think so.
yeah, I mean that's also my understanding. It's a 2060. And to achieve that target, hydrogen can play an important role. And the application for which hydrogen might be popular because you cannot use direct electrification for all application. So the cases, I mean, you can use direct electrification. I don't think, hydrogen might be popular for, I mean, those cases, but still, I mean, there are many cases that you cannot apply, direct application for all of our energy application. So that's why, I mean, hydrogen has got a, I mean, great potential, and as I say, like, it would be a important candidate to achieve the net zero target. Now, I mean, so far in Australian perspective, I mean, Australian government, they have done some study and they have predicted that next, like, within 30 years, so the hydrogen market would be, I mean, approximately $50 billion in Australia. And that will help not only Australia, but the world to achieve that, deep decarbonization. But if you think about, or if you ask me about the current situation, what I said that this is a long way, like, from producing cheaper green hydrogen, which can compete with the fossil fuel. But as I say, like, by 2040, not only in Australia, but in many other countries, they predicted that, almost like 83% fall in electrolyzer cost. And that will help to reduce the, per kg hydrogen significantly. Now here, I mean, so far in Australia, I mean, these are the some of the lowest price that's available in, in different state, because the electricity price also in different state in Australia. That's why, I mean, so far I think the Queensland and Tasmania, they are the leading in terms of the lower price. But as I say, like by 2040, it is expected that it would be like, like 1.7 in Queensland and 1.8 in other countries like New South Wales, Victoria, and South Australia. So if you can achieve that target, in that case, I mean, it would be comparable and it can compete with fossil fuel. But this is not only in Australia, it is a global trends. So far, I mean, more than 30 countries, they have already released their hydrogen roadmap for the next 20-30 years. And there are many reports are also available from Europe, IEA, International Energy Agency, and also Hydrogen Council. And for Hydrogen Council, already there are 109 members, and that members is growing day by day. So what I'm trying to say that the hydrogen will play an more and more important role in energy transition in coming years. And this is just like the hydrogen map for Australia, and these are showing some of the potential location in different parts of the Australia. And here in also New South Wales, I mean, we have got some location, potential location where we'll be having, hydrogen hub. So you can see that, I mean, in Australia wide, Australian government have already targeted, I mean, many potential location. There will be having like, hydrogen hub in those particular location. So In longer term, as I say, like, high capacity storage will be needed. And to store as well as transmit, we need more massive technology. And as I mentioned, like, so far there are a number of research projects going on worldwide. And I believe by, 2030, 2040, we'll have massive technology for hydrogen production, storage, as well as transportation. And again, these are the roadmap for Australia for hydrogen is, starting from 2023 to 240. So by that time, as I say, I already showed those particular location. They have also predicted the hydrogen price in different location, and as you can see that with progressive time for all the location, hydrogen price will be reduced significantly. The same thing has been done for Europe, USA, China, and other countries as well. So I think for USA, they have, for Europe, they have predicted that by 2024, they will be having 6 gigawatt of renewable hydrogen electrolyzer and 40 gigawatt of renewable hydrogen electrolyzer by 2030. So there will be like an exponential increase, in Europe as well, and that will definitely, help to reduce their greenhouse gas emission by more than 50%. Like in terms of, in India, I think all of you are familiarized with this theory, the Energy and Resource Institute. I think that's probably in Delhi. So they have done, some studies on hydrogen, and from their findings, they have found that in India, the current price is $5 to $6 per kg, which is definitely much higher than in Australia now. So with this price, it is unlikely that it would be possible, to utilize hydrogen in different countries, for example, like the steel, fertilizer, or even for long range shipping fuel, EV application as well. Now, green hydrogen to be feasible in India, so they mentioned that so at least the price should come down to $2 per kilogram. But having said that, I think their final target to bring down the price $1 per kg. But definitely, as I said, this reduction is not possible now, and it will not be possible without, manufacturing electrolyzer on a broader scale in India, not like exporting from other countries. But still, there is a great potential that will happen in India, because Indian government, they actually spend huge money. It's like over 160 billion just to import coal and oil from other countries, and it is expected that even that might increase 2-3 times by 2040. And not only that, if they continue to produce electricity from this source, it will have a catastrophic environment impact in India. I already know that there is already issue with air quality and so on in India, because I have been to Delhi a few times, and sometime I found that the air quality is very bad in Delhi. So I mean, for environmental purpose also, I mean, there is a, I mean, like great potential of having hydrogen, like in a massive scale in India. Another reason, as I already mentioned, that if they would like to go for, I mean, net zero by 2060, I think only having, I mean, some technology will not help to, you know, achieve that targets. It needs like a more like systematic and mix of technology. And for that, you know, hydrogen could be playing a potential role in energy transition, for example, in transport, for long range vehicle and heavier truck, I mean, heavier duty trucks. And it could be other sector for like, you know, chemical feedback and even in the power sector as well. So far, I mean, in India, all the hydrogen, I mean, they produce, that's coming from fossil fuels. So you can see that's, it's mainly coming from like, you know, ammonia fossil, methanol fossil. So all of them are coming from fossil fuel. Nothing is coming from green hydrogen. But as I say, like, you know, after 2030 and even like, you know, 2040, I mean, the other form of hydrogen would be popular because the price will go, will go down significantly. And you can see like, you know, sorry. Sorry for that issue here. And you can see that after, I mean, 2040, there will be like a massive growth, I mean, in India. So in terms of the pricing, like comparing with solar, natural gas, coal, and grid electricity, you can see like that, you know, off-grid solar also like, you know, would be very comparable to, you know, natural gas as well as coal. So here, I mean, they have given like, you know, some roadmap for India, like, you know, what might be happening in the next 20-30 years. And again, I mean, he had just mentioned like what will be making inside India, what are the possible, you know, industry that will have potential for you know, using green hydrogen. And as I said, like, you know, what could be the like, you know, possible demand by 2050. But anyway, I mean, if you have just time, please have a look the slide. I mean, it's quite generic information. And this one just mentioned like hydrogen demand, just considering like, you know, business as usual. Like if you just consider baseline, probably that would be the demand. So this is like for 2020, and by 2050, if you just follow this trend, that would be probably the, you know, hydrogen demand. But if they follow that you know, net zero or low carbon path, I think that would be the demand, because in those cases, I mean, to achieve that target, you have to have higher, I mean, you know, source of energy from, I mean, green sources. So that's why, I mean, if you follow that low carbon path, even that, you know, demand would be higher. Now, there could be, as I already mentioned, there could be a number of objective. I mean, for having hydrogen, it's not like a single objective. And here it just mentioned, some of them here. So it's like a clean transport. That's, I mean, we already talked about that one. Storing hydrogen for grid balancing as well. It's not only producing hydrogen from, solar or wind, but at the same time, as you know, that solar, wind are, variables. I mean, battery could be, potential source for storing energy if you would like to do it for a short period of time. But if you would like to do it for a longer period of time, that hydrogen storage would be better than the battery. So that's for, grid balancing also. Hydrogen could be a, another alternative source of storage. And then, heating and cooling demand, that also could be, fulfilled from hydrogen as well. So recently, we mainly use gas for heating and cooling in Australia, and also, in many other countries as well. And as, one of you mentioned, like, power 2x, and to that, hydrogen could be a potential technology to do that as well. So power to, could be, any source of, like, application. And here, I just mentioned that, from power, you are having hydrogen, and then you are, using hydrogen for so many, applications. It could be like in the different industry for mobility, and also for stationary energy demand as well. But it could have, this is like, it's mentioned like, almost all sector, not all. And here it's just mentioned like, some of the application to power to X. For example, one of them would be that, decarbonizing the heavy industry. And to do that, we could utilize, those source of energy to produce large scale hydrogen through that, electrolyzer. And then we could have, hydrogen, which could be used for, like a combined heat and power plant in different industry uses, and also like, as I say, like, for like use like ammonia export in different countries, steel industry, cement industry. It could be also for synthetic industry. And here are some of the example. It could have like, again, on the chemical precursor, industry feedstock, power generation, aviation fuel, and also other application could be like, some decentralized application. For example, if you have a off-grid, like in a small remote or microgrid system, you could have like a decentralized hydrogen refueling station. You could also have a like, standalone ammonia production for greenhouses, or you can also have like an on-site disinfection system as well. So there are, and this is like some of the application, but there could be many other application as well. So here again, I already mentioned that it could be for fuel cell in transport as well as energy. It could be a, other sectoral integration. And here some of the sector I mentioned, like, steel industry, refinery, mobility, and it could be interconnected to the gas grid as well. It also could be utilized to greenize the steel industry, because that's industry now is heavily, producing a greenhouse gas. It's a polluting industry, and to make that industry green, there are already in Europe, there are a number of project is going on. And as you know that, I mean, the electrolyzer is like one of the main technology for producing green hydrogen. So there are like, there is like a push for going for a higher capacity of the electrolyzer with definitely, higher performance. And to do that in Europe, actually currently number of project is going on, but this is showing like, 3 of the project. Now they are, actually trying to improve the performance of the electrolyzer. And also like they're also having project for other application as well. And here it's just mentioned some of the application in Europe. For example, here like domestic and commercial end users. And also like here having very high pressure gas network and power to gas system. So as I mentioned, like power to X. So here they are also doing power to gas system. Now, as I mentioned like that, I mean, there are like, different pathway to produce as well as, store hydrogen. And here just mention like some of them having, producing hydrogen either from nuclear energy. And from nuclear energy, you can have heat, and then you can just use that heat just to split the water and having hydrogen. You could also have renewable energy sources. That's we already in Abbas talk in details. Having either directly through electrolyzer using electricity, but also we could have like other method, for example, photo electrolysis. So there could be some special semiconductor materials that you could directly have sunlight from that, and through like chemical process you can produce hydrogen. You could also use some microorganism, and through biological process you could also have hydrogen. But each of all the technology, they have got their own advantages and disadvantages. You could also use biomass, and then gasification and reformation. You could have hydrogen as well. And this is, as I say, like already we are having hydrogen from fossil fuel as well. So again, I already mentioned, but this could be some of the sources where you could use electrolyzer to produce hydrogen. For example, you could have solar PV, wind, hydro, ocean energy, or geothermal. All of them are renewable energy sources. So you could use any of them as an input energy, and then using electrolyzer, you could produce hydrogen. But and here also Abbas already actually compared that one. I'm not going to talk about that again. But currently, this is the mature technology. This one, probably coming soon, and it would be even like popular in coming years, because it has got some advantages, but at the same time it has got some disadvantages as well. This one have not been still commercialized, so this is mostly like under research phase. And as I said, like for electrolysis, there are number of projects going on all around the world. And here, as I said, like in United States, Canada, China, Australia, but they're also having like Japan, Korea, even in Saudi Arabia as well. And this one actually showing that electrolysis pathway, and that's the example that's coming from Europe. And as I said, like they are expecting like having like at least 40 gigawatt capacity by 2050. That is like, in EV internally, but even they consider you internal, external, even that would be, higher than that. So if you have like, using sunlight, but you are not using photovoltaic system, there are also, three other different way that's I already mentioned, that you either using heat, that is either directly, capturing the, sunlight from the sun using your solar thermal system. So you can have a like, big like glass, and that will capture the heat, and it produces actually very high temperature, and you can use that temperature to split the water and produce hydrogen. You could also have nuclear energy and then produces heat, and then you can produce the hydrogen. Photo electrochemical, as I mentioned, there are some materials which if you have directly, they can capture the sunlight, and then using anode cathode, internally also they can produce hydrogen. And then, as I mentioned, like then if you have got a microorganism through a photobiological process, it takes the sunlight and it produces hydrogen. But here the capacity and the rate of hydrogen will be very low compared to other cases. As I said, biomass could be other potential source as well. And these are the three processes, you can utilize to have it from biomass. That slide I'll just skip because I already mentioned that application for transportation. The storage of Abbas had already talked about that, but here is just mentioned some of the challenges. For example, if you want to have liquid hydrogen, your temperature should be like minus 253 degrees centigrade, and that's quite challenging. The geological tank, all of them I have Abbas already mentioned. So next, I'll just, although like 8:30, maybe I'll just take another 5 minutes, just to go through that particular application. So as I mentioned, we done a feasibility study to just having a hydrogen hub at a place where it's called Sydney Science Park, where we'll have a huge demand potential for that particular area. And to do that, we just have done some application, and these are the potential application that we have just considered. Like it have a large office space, mall, super mall, office, restaurant, office space, school, and also like there'll be like one airport. And then considering that current electricity price in that particular area, here is just showing the electricity price for a particular day in a particular month. And then in the same month, we have considered what could be the potential demand for all the load that I mentioned, which will use hydrogen as their source of energy. And then we developed some optimization algorithm to find all the new technology that we'll be having in that particular area. And also it will be having some hydrogen storage production capability. And as I said, it will be also having hydrogen refueling station and also many other application. So here also, we just consider two cases. One is like if you consider business as usual, as well as if you consider like net zero path, what could be that sizes of different devices, what could be that initial investment they might need, and also what could be other associate cost. And this is just like the complete diagram for the system that we have modeled, optimized, as well as simulated. And here we're just showing like three different terms: short term, medium term, and long term. And for short term, what could be like different opportunity for generation side storage, as well as demand. So we consider like 3 different phase, and we estimated model as well as simulated for 3 different cases, considering different like source as well as mix of generation, storage as well as uses. And then we have found there like as I said, like we have simulated 2 scenarios for 3 different terms, and here we have calculated like their hourly demand, usage, storage, and all the result have been shown here. And as I said, like I have already given the slide. So this is like some numbers. When you have got time, you can read it. So even in your case, if you would like to do like have hydrogen hub in any part of the India, definitely they will be doing initially the feasibility study, and these are the concept probably you can utilize to do that. And finally, we have come up with like cost for investment, operation, maintenance for like different technology, for example, like PV, electrolyzer, storage, different application, as I mentioned, like hot and cold storage, and so on. So that's all I would like to share. Sorry, I have gone like a few minutes over time. But if you have got any question and comments, let's feel free to share.
Do we have any questions?
Do you have any final question or comments? Okay, if not, I think it has given you at least some understanding and also some idea about what are the current as well as future challenges, opportunities, and also some of the research problem that you can think about if you would like to work in hydrogen area. Anyway, if you don't have any question today, so I think I already mentioned to Altaf, but for the next 3 days, tomorrow, again, initially, we'll be talking a little bit slightly different, because so far we have only focused on the generation side. We have not talked about like the customer as well as the market side with a different like the new technology that's coming. So we'll have some one presentation on that, and then the rest of the time I'll be talking about another potential technology, microgrids, that you already heard about that. And in the final day, probably I might to run some problem solving question. I'll just give you some question that you can think about how you can analytically solve. So that will also give you some idea. If you would like to do research, because in some part also you need to use some analytical model in your research. So with that, if you don't have any question or comments, thanks for your attention, and I'll see you tomorrow.
Thank you, sir. Thank you very much.
Thanks. Thanks, everyone.
So we'll
Bye.
be closing today. Yeah, thank you.
Thank you.
Okay, sir.
Thank you, sir.